Hello everyone, today is the day 14 of 75 hard research challenge and I'm going to talk about what I did yesterday, that is on day 13th. So I studied QLoRA, which is quantized low rank adaptation, and this is used to fine tune large language models on a small GPU. So let's get started. Okay, so let's first go through what are the basic quantizations. A detailed discussion on quantization was shared in the last video. I'll leave a link in the description of that also. So what is basic quantization? For example, we have absolute max quantization, where we just the quantized value is simply the real value, the actual value, original value divided by the max of all the values possible. Similarly, absolute mean quantization would say that you just divide the real value by the mean of the all the values possible, right? Okay, there is something called 1.58 bit large language model. Recently the paper had caught up some hype. So it is a quantization aware training approach, where there are two approaches. One is first is post training quantization, and second one is this QAT, that is quantization aware pre-training. So in the post training quantization that we are going to see next or in the like in the lecture, what they do is that first you train a model and then this you simply quantize it either in simply by taking a higher data type like floating point 32 and convert it into floating point like let's say 8 or 16, or brain float 16, or you can simply convert it into int 8, and nowadays even in int 4. Okay, so this is a 1-bit large language model. This is a paper that focuses on quantization aware training, where simply what you do is that for each weight matrix w, you are going to pass it through a function that is going to convert it into either -1, 0 or 1, right? These three values will be fixed for a particular weight, right? How do they do it? They simply whatever weight matrix you have, you divide it with the mean, right? This epsilon is added for computational stability. That means to avoid, if the mean is 0, that you avoid division by 0 in this case, right? And what you do is that you want to convert your number, if this is the number line 0, -1, 1, then all the numbers should either be 1, 0 or -1, right? So that's what you do. You first see, you take let's say in this case b is equal to 1, a is equal to -1. So you see whether your number let's say -1, 0, 1, whether your number x, if you take a min between b and x, that means if your x lies here, it will be converted into 1, right? And let's say the x was here somewhere, then it will remain as x. Okay, so then you take a max between a and x. So if x is greater than a, that means -1 in this case, it will remain the same value. But if it is less than a, it will return to -1. And once you have done it, you'll either have -1, 1, and -1 for all the values here, 1 for all the values here, and x for all the values in between. And then you simply take a round. You clip it and round it. So it will either fall to -1, 0 and 1. Okay. So these are the some very basic forms of quantizations that are possible. Let's focus on QLoRA, which is the primary focus of this particular lecture. So I'll walk you through a couple of screenshots and give some intuitions behind it. Let's first see what is the task for QLoRA. So in the case of QLoRA, what we have is that let's see what this particular table signifies. You have a model in the first column. You have the amount of inference memory taken in the second column, and fine tuning memory taken in the third column. That means inference implies that you do not back propagate, you simply do a forward pass. Fine tuning would imply that you have to do a forward as well as a backward pass, right, on a pre-trained model. So if you use T5 11 billion parameters, it takes 22 GB and 176 GB. If you have LLaMa 2, now recently they have released LLaMa 3 also, like 2-3 days back, I think a week back or so. And if you use LLaMa 2 7 billion parameters, for inference alone it will take 140 GB, and for fine tuning it will take 840 GB, right? And that's a problem. That's a problem because if a normal human being like you and me cannot train all of these, right? You cannot leverage the power of a llama 2 model, llama 3 model. Usually what people do is that they use llama 7 billion, right? So they say that if you use QLoRa, that is their approach, this memory requirement will reduce to something like this, that for T5 you will need now 5 GB only, in comparison to 20 GB, and 6 GB for fine tuning, right? There's a huge drop in this case, right? Similarly for llama 2, 33 billion and 70 billion, there's a humongous drop in the memory requirement. For example, if you just want to do inference, you can use llama 2 model very easily, llama 2 33 billion very easily on your on a standard GPU that you have, customer grade GPU. Okay, so before we go to QLoRa, which stands for Quantized Low Rank Adaptation, we will first see what is low rank adaptation. Okay, so low rank adaptation is a simple phenomena. Let's say let's say you have a weight matrix. Let me draw it a little bit above. So let's say you have a weight matrix with you W that you want to fine tune. It is already pre-trained, right? So now let's say if this is a m cross n matrix, then all the weights of these matrices need to be updated, or can be updated during the back propagation, right? You will do forward pass, and then while doing the backward pass, all these weights will get updated. So it was noticed that the weight matrix of the gradients was a low rank matrix. That means that it can be represented using a low rank matrix, where what is the rank of a matrix? The rank of a matrix is the number of linearly independent, this is a sign for independence, linearly independent rows or columns. Okay, so they notice this, and they leverage this fact by saying that if you want to particularly update this, then what you do is that you freeze these weights as it is, and you add two more uh, matrices. One is A, let's say, or let me just use the nomenclature used in the QLoRa paper, that is L1, and another one is simply L2. Okay, so L1 and L2 are two low rank matrices. Okay, so for example, the L1 will have a dimensionality of m cross r, real values, and L2 will belong to real values r cross n, so that when you multiply L1 into L2 matrix multiplication, you will have r m cross n with you. So now this W as well as this multiplication of L1 and L2 can be added together to do some form of inference, because they are of the same shape, right? Okay, so that's what they do. They say that for a projection matrix this, with x belongs to a B batch size and h is the hidden dimension, we simply compute LoRa as y is equal to xw, which you were supposed to do. That means for the pre-trained weights W, you pass the x to it, and you pass x also to L1 into L2, which is also a m cross n matrix, right? And then you add them together with the multiplication of S, where S is the scalar that wants to control how much effect this L1 and L2 needs to have on this final computation Y. Okay, so what are they doing? They are saying that during training, what they are going to do is that they are going to freeze the weights W. That was the pre-training weights are frozen, but the weights L1 and L2 are trained. Okay, so now you can see that earlier what would have done is that would have trained W directly, so we would have had m cross n parameters with us. But in the case of this particular approach, that means LoRa approach, what you will have is that m cross r plus n cross r number of parameters that are going to be trained. Now this rank r is usually kept very low as compared to the size of m cross n, right? M or n, right? So that means that m or n, right? So that means that the number of parameter drastically reduced when you use LoRa. So this was fairly popular and people used it. So let's see a comparison between fine tuning and LoRa, and then we will also see a comparison between QLoRa. So let's say you have a transformer model with you with 16 bits used as a data type, and similarly you have an optimizer with 64 bit, and let's see what is the memory requirement for this. So let's say you have for each parameter to be represented, corresponding to each parameter, we have 2 bytes for weight, 2 bytes for gradient, and 8 bytes for optimizer state. That leads to 12 bytes per parameter. So for a 70 billion model, we will need 840 GB of GPU, right, for fine tuning. And this is not possible for a person like me and you and even academic institutions, right? So let's see what happens in the case of LoRa that we just saw. So in the case of LoRa, what they do is that they keep the base model as 16-bit transformer, but they, rather than optimizing the weights directly, what they do is that they have adapters with them, and corresponding to each adapter there is an optimizer state. So based on some mathematics, as I was going through the talk of one of the lead author of QLoRa, they say that weights now required 16 bits, and which is 2 bytes as earlier. The weight gradient now requires around roughly 0.4 bit, 0.8 bit and 0.4 bit per parameter. The reason for that is because we are using low rank matrices here. So when you take the average and divide by the number of parameters in the model, this is the number that comes out. So in total you need 17.6 bits, which was earlier 12 bytes, right? So a 70 billion model now turns out to be 154 GB of GPU memory, which is again a humongous amount of memory that a normal human being or a person with consumer grade GPUs cannot leverage, right? Okay, so in the case of QLoRa, we haven't discussed what is QLoRa, but let's first see what happens when you have QLoRa with us. So what they do is that they keep the transformer model in a 4-bit quantized version, and they keep the adapters in the 16-bit version, and they keep the optimizer again in the 64-bit. So the precision of these 3 blocks increase as we go from bottom to top, right? So based on this, you need 4 bit for per parameter for the transformer. Similarly, you need 0.4 bit and 0.8 bit as earlier, right? And 4 bit for adapter weights as earlier, right? So this turns out to be 5.2 bit per parameter, and roughly translates to 46 GB of GPU memory, which again is a bit difficult to train for a person like me, but still it is much less than, let's say, 840 GB of GPU memory originally without LoRa and QLoRa, right? So now let's focus on what is the quantization method being used in the case of QLoRa. So let's see what is absolute max quantization that we saw earlier in the same lecture. In this, what we have is that, let's say you want to convert a floating point 32 into integer 8. So how do you go about it? You say that the maximum value of floating point of integer 8 is 127, right? And you divide it by the absolute maximum possible for floating point 32. A good way to visualize this would be, this is for floating point FP32. This is, let's say, int 8. So what you are doing is you are essentially shrinking these two here, and somewhere there is a 0 point, and that maps to the 0 value here, right? Okay, so how do you shrink that? You simply take the scaling factor, which is also called as quantization scale here, right? Quantization constant or quantization scale. Sometimes it is represented as C, sometimes it is represented as S for scale and constant respectively. Sorry, constant and scale respectively, right? So what is a constant? Simply it is that what is the possible value in int 8 divided by possible value in floating point 32, right? So you multiply your floating point 32 value with this quantization constant, and you round it because it is an integer thing. Integer lower data type is of integer type, so you get the value with this, right? The problem with this is that, let's see what is the problem with this sort of quantization. Okay, let's say you have a probability distribution like this that you want to quantize, right? It's a continuous value. So what you do is that you simply divide it into 16 bits, right? And you get these particular bins with you, right? So what happens is that while these models most of the weight in the CDF, right, in this PDF. What if we get an outlier like -9, -8 or -7, right? So this cannot be represented at all, and usually it is mapped back to the lowest quantization that has been done so far, right? And that's a problem. So to give a solution to this sort of problem, what people did is that they proposed block quantization. In the case of block quantization, what you do is that, let's say you have these particular numbers with you, all possible parameter values. So what you do is that you divide this into blocks, right? Let's say in this case we have divided it into 3 blocks. Okay, this block, let's say 4 blocks. Okay, so what you do is that you have a normalization constant separate for each of these blocks. That means earlier what we had is a single normalization constant C that will map the complete range into a quantized range. Here what we did is that we have a separate binning process for which we will map these separately. So in this case, in this PDF diagram, what it will translate it into is that you will have a separate bin for this, maybe a bin for this, maybe a bin for this, right? So now these values can be mapped easily and quantized differently. Okay, apologies. So what they do is that, so there are 3 innovations that they do. Okay, so this block quantization is not their innovation. That means they are not, this was proposed earlier, I think, by the same set of authors, that rather than having a single constant, quantization constant, you have 4 different quantization constants. So not only this, what they suggest is that you also do something called normal float for quantization. Okay, so in this case, again, as I said that not only do you have blocks with you, you make sure that each of the blocks map from -1 to 1. Okay, so when you normalize this particular bin individually, you make sure that each bin is now mapping to -1 to 1. Okay, second, or rather, let me just walk you through an example. Let's say you want to have 2 bins out of this, rather 4 bits. So you have a 4-bit normal float with you, right? So you want to represent floating numbers but in only 4 bits. So how would you go about it? So 4 bits would represent 16 different values, right? So that's what you do. You divide, all the parameters are now converted into a normal distribution where with mean is equal to 0. And then what you do is that around the mean you divide 2 parts. Okay, in the first part, on the positive side, you have 8 unique values. On the left side, that is on the negative side, you have 7 unique values. So why this dissymmetry? Because this adds up to 15 only. Asymmetry, because it adds up to only 7 here and 8 here implies 15. So one value is missing, and that is being used for 0. So how do you go about it? On the left side, from -1 to 1, you divide these you quantize these values with equal gaps here also, right, on the positive side. Then what you do is that you calculate the negative z values for this. Z value is nothing but you renormalize essentially these values and multiply these by -1. In this case, you multiply it by +1, right? Once you have this, you add a 0 value and concatenate these two and then renormalize again. Okay, so now these are the values that are the final bins or final values that any new number or any new parameter can map to. Okay, so this is the first innovation that they did. Second innovation that they did is called double quantization. So they propose, or rather they argue that in the case of, let's say you have a weight matrix of 8 bit, you quantize it to 4 bits, right? Now you have to store the quantization constant also. So if you have, let's say 64 parameters with you, Okay, so for every 64 parameters you create a bin. Okay, so that means that you will have a certain number of rescaling constants with you. To represent all these rescaling constants, you will need a 32-bit value again. So right, so when you quantize this particular weight into 4 bits, or you also add an overhead memory in the form of quantization constants, which will add up to 0.5 bit per parameter. Okay, so what does that mean? How do we come up with this equation? We simply say that for every 64 unique parameters, you use 32 bits. So for each parameter you used, 32 by 64 is equal to 0.5 bits, right? So half a bit is being used. So when you do it for 70 billion parameters, it adds up very fast. So what you do, you quantize these particular constants also further to a second level, hence it is called double quantization. Okay, and this adds up to roughly 0.002 bits and 0.125 bits for this. Okay, now they also do some new innovation. There is a third innovation called page optimization. So what happens in the case of normally training a large language model is that sometimes the sequence lengths are not always of the same size, right? For example, if the model is generating something and it is being trained on a masked language model or an autoregressive fashion, what happens? Sorry, not in the masked language model, but in the case of autoregressive decoder only architectures, what happens is that as the context length increases, or your own generation is being fed again into the model, then this can lead to very long right length of sequences, which can lead to more GPU memory than available. So in this case, what they do is that they shift some of the uh, uh, optimizer weights or optimizer variables into the CPU, and then process or do the forward pass and backward pass, free up the memory, and then bring it back again if needed. Okay, so this is the final innovation that they did, and they say that this led to great results. I'm not going to go through the results in this video. You can check out the original paper. Okay, so that's it for quantized LoRa, and we saw that in comparison to LoRa, it further reduces the memory requirements, and this led to great results without much difference in the performance. Thank you.